What daily routines or tasks would you like to automate? In this episode of Root Access, we talked to Zora Wang of Carnegie Mellon University about her paper, Agent Workflow Memory, a method for inducing commonly reused workflows to solve real-world tasks like web navigation. Don't forget to like this video and subscribe to the channel. I also have an interesting poll linked in the description. Be sure to check it out.
Hi, Zora. Thank you again for joining us today. Before we dive into the details of your paper, I'd like to start just by understanding a little bit about what drove you into the field. You're at Carnegie Mellon working on your PhD. What drives your interest in this field?
Yeah, so more generally, the reason why I'm interested in machine learning AI, or more specifically natural language processing, is I want to build systems or AI-based machines, whatever you call them, to help humans do their jobs, or at least on the repetitive part that humans don't actually want to do. So in general, just to build AI tools that can really facilitate human life.
Yeah, that's one of the things that stood out to me about your paper, something that drives my interest in learning more about what you're working on, because it's very user focused. I can see the real world benefits for myself as a user of something like agent workflow memory. I think that connects to your motivation with this paper. Can you talk a little bit specifically about what led you to work on this topic in particular?
So I've always wanted to do more real world tasks using code generation. So actually before this, a lot of the tasks we're doing are solving math problems, were table-based question answering, which are also pretty realistic, but you still have some distance to deploy that in your like products or real world systems. But for this agent thing, is actually you can imagine that as a Chrome extension in your browser. And if you just open your computer, you'll directly use that agent on your computer. So it's more connected to the real world life that we have. So I think that's one particular reason I'm interested in this web navigation agents. Yeah, and another thing is like more challenging than other tasks because the website environment that the agency uses is changing all the time, and the tasks are usually more complex. You need like tens of steps to complete, like to buy something at Amazon, for example. So yeah, like technical wise, it's also more challenging for researchers or industry people to work on this problem. I think the simple goal is to build more high performant agents, but also the nature that this task is more real world oriented and this more complex makes this problem more interesting.
So in this paper, what problem did you set out to solve?
Task is mainly that I dealt with web navigation. So basically, on the input side, you can imagine that user says a query or an instruction like buy cat food on Amazon and deliver to my address. And the user only needs to provide this natural language query. And you ask the agent or the language model to do basically produce a series of actions like click this button or type some other things in this text box to do a series of these actions to finally do the thing they asked it to do. It will add this cat food to your cart and then deliver to your address, things like this.
Walk us through a little bit of the paper. Give us an overview. You set up a couple experiments. Tell us about those and then the empirical results.
Mm-hmm. Yeah, so more specifically on my paper, I think the motivation is targeting on more complex and long horizon tasks, which you may take like 30 steps to do one task. Maybe you ask the agents to create a GitHub repository and create a new file, but in the new file, put in the top five Reddit posts in some forum. So you need to look over multiple websites and do it in a very long term. So the motivation is that current agents can do some easy tasks, like for example, add an event to your Google Calendar. But for this complex long horizon task, it's still very challenging for them. My motivation is sort of driven from how human would learn these different tasks. So
Mhm.
for this complex task, like the multi-website setting, is like similarly complex for humans. When you're doing 10 steps, you forget what you want to do next or what you've done before. So sometimes the human approach, or at least for me, is you divide that into multiple subtasks and you learn from your past experience that, for once you do a easier task, you only need to create a repository to learn the subtask. And another time you learn another subtask to find the top ranked posts in Reddit. And after you learn the subtasks, you compose them based on the request of your more complex and long horizon tasks. So the workflow actually in our paper means the subtask level, which are reusable across different tasks. So the fundamental approach is for the agent to learn things on this workflow level instead of on the entire complex trajectory level. So it's more generalizable. You can just easily compose different workflows every time when you encounter a new task. So, from another perspective, there are also works that try to manually using human experts to write the subtasks and provide those to the agents. But our approach here is to ask the agent itself to observe its past experiences and induce this workflows themselves. So in this way, it's more scalable. You don't have to rely on humans to do anything. Imagine you have a new website that you want some workflows for it. You don't always have to ask a human to write it beforehand. You can just run your agent and it will do everything. So that's the methodology part. And I think I always draw analogy to the human brain. We also learn things on this reusable subtask level and learn to composely apply them to new tasks. And a bit on the experiment side, we just designed this method and compare it with previous baselines, and it did show a big improvement on the two major benchmarks that we evaluated. So yeah, it sounds like a promising approach.
So let me test my understanding a little bit. So the initial set of tasks is human driven, and then the agent will learn from those subtasks and ideally be able to apply them to novels, scenarios.
So actually, I have two settings. One is called offline setting, similar to what you described, that you have a set of human annotated examples beforehand. Say, usually these examples are pairs of natural language queries that users asked and the set of actions that the agents supposedly take to solve the task correctly. And in this offline setting, we call it offline because we ask the agent to first learn subtasks from this provided set of examples. Say, from this examples, my agent learns search a product, add to cart, and check out the subtask. And then at test time, we have a set of different queries, but no annotated action. So the agent just uses previously learned workflows to apply it during test time. So that's more like it learn from human annotated examples. We also have another setting, which is called online setting, where this set of pre-annotated examples are not provided. So you don't have any knowledge about this website or any task at all. And you just have the set of task queries. And what we do is the agent process each query at a time, but it will generate a series of actions trying to solve this query. And we have an evaluation module. If that's evaluated to be correct, we'll just take that as a correct example that the agent should learn from, and they'll induce workflows from its own past experiences.
Interesting. This could be trained on what the preferred workflows are and suggest a workflow, and then it could just do it for you.
Yeah, so there are two ways that you can generate some workflows. One is human curiously designs of workflows based on their observations or any other preferences. Another way is more what we do in this project is ask the agents to use workflows themselves. So it's mostly like a data-driven approach. This
Okay.
look at what examples are out there and summarize workflows out of them. I think both approach can be used together, but it's just dependent on what you have and what efforts you want to put in. So if you don't have good human experts to do things for you, you might want the agent to do it themselves. But if you have some requisite on the agent were some good observations, you can also augment that yourself.
The generalizability, like you said, was one of the main goals. Elaborate a little bit more on what that meant for your design choices, both for the setup and also for the experiments. How did you prioritize that in the workflow design?
Yeah, so for first on the dataset side, we use two datasets. One is called Web Arena, another called MindWeb. Both websites are pretty like commonly used, but they have slightly different emphasis. For Web Arena, they only have 5 websites, but for each website, they have 100 to 200 tasks. So that gives you more variance in the that you can do on the particular website. And for a mind-to-web dataset, emphasize more on generalization, but more in a way that's like generalizing across different websites or across different domains. Say, for example, in the training set, we have a task for Amazon website. Across website scenario would be like in the test set, we have a Target website, which is both shopping, but just particular for different like companies. And also further, we have like cross-domain generalization, where, for example, still, if you have shopping Amazon in your training set, in the test set, we might have United Airlines, which is for travel domain. So this like a bigger gap. And on both data set, we basically did this 3 level of generalization. One is cross-task, which is within a website, do various different tasks. And second is cross-website, and third is cross-domain. And for the methodology part, we have 2 specific designs on the workflows that intends to make it more generalizable. One is the subtask level, granularity level that we choose to maintain. For example, search a product is more generalizable than search a product, add to your cart, and checkout. So the like intuitive one. And another is we try to abstract out the example specific context. Say in this example, I have buy cat food and deliver to my address. The workflows that we end up generating will be search a product instead of search for cat food. So that could really help to generalize to other tasks. Say next time if I want to search for a water bottle or anything. Yeah, so I think that's basically the approach. And it does show like good generalization abilities across this different cross task, cross website, and cross domain scenarios.
Yes, share a little bit more about the empirical performance.
I'll just go over each data set. For Web Arena, first, overall, we just compare with previous baseline methods, and we got almost a 50% improvement. So that's a really high increase. Where maybe I should say a caveat of the website Web Arena benchmark is that the creation process, they actually create a bunch of templates at first, like, for example, by product name on Amazon. And then they instantiate this template with different values and create, say, 5 examples with this template. Say they could create buy cat food, buy water bottle, or buy napkins, things like this. So you can imagine, for example, if I induce a workflow from buy cat food and I induce like a search product workflow, then I could very easily generalize to other tasks that are instantiated from the same template. So we want our methods to generalize to not only work on the same template examples, but also work on cross template examples. So one thing that we did is we randomly sample one example from each template group and create a subset of Web Arena and only run our method on this subset, which they don't have task overlap. But our method could still improve a lot from the baseline. So one thing that we noticed that our method can also realize this cross template, or it can call cross task generalization. One interesting thing that I observed, which is actually the teaser figure, the figure 1 in our paper, that we have this like a growth line they can plot over the course of the model doing this induction and using workflow. So what we noticed, the model started learning some very easy tasks. For example, if I'm on the map website, then it will first learn how to find a place by its name. It will just search for the name of the location. And then gradually it will learn from this and learn some more complex tasks like find the zip code of the place. So to do this, you first have to do the steps of finding this place, and then you do a few steps to get the zip code of this place. And similarly, you can grow the workflows. It's similar to human that you start learning some easier things and then gradually compose them with some new steps to build it as a like more complex workflow. So I found that particularly interesting. So this like continual learning more complex workflows, I think is the key to do this cross-task generalization. So that's on the web brain set. And on the mind2web data set, they just intentionally designed the test set to be spanned across different websites and different domains. Yeah, actually, the remember that I mentioned we have two settings, offline and online setting. We did an interesting comparison on this method, especially on the 3 different generalization tests. So imagine there's an axis of the train task gap. So the gap between the training example, which are the examples that you've seen, and the test example, which the model only see at test time. So where cross task has the smallest gap, and in the middle is cross website, and then finally the cross domain has the biggest gap. And when we test the offline and online methods on the 3 sets, we find that initially when the gap is really small, the offline method performs a bit better because it's like learns more directly from the training example and can directly apply it to the test example. But when the gap continues to grow, we find that online actually in turn outperform offline methods because it does is not affected by the training example. So when the gap is really big, maybe the training example gives you too much bias, but it's not actually applicable on the test examples. So we see this different performance of online and offline methods when we have different train test domain gaps. That's an interesting finding too.
Yeah. And so you also talk about BrowserGym, and
Mhm.
you use that as a comparison in the experiment, but you alter it. I guess first, for people that are maybe not familiar, what is BrowserGym? And can you talk to us a little bit about the rationale to alter it and whether you think that introduces any kind of limitations to the study?
Mhm. So first, BrowserGym is just a like commonly used platform where like a code base you can run this different agents, including agents on Web Arena dataset. The reason why I chose is just it's easier to use. I think for now the easiest to use platform. The reason why we altered it is for the initial Web Arena paper, the observation space of agents is the what they call accessibility tree of the web page. So it's like a you can imagine that as a tree structured way to list out the elements in the website. And the modification they did in BrowserGym is they provide both the accessibility tree, which is used in the web arena baseline method, and they additionally provide the HTML code of the website. And basically, the reason why we altered it is sort of like a Bayesian study that we want to see if we only provide this accessibility tree, how good can this platform gives you. So yeah, that's more like a Bayesian study. But also due to the concern that if you both provide accessibility tree and HTML, the context length will be like thousands of tokens very long, but not sure how much improvement that could give you.
Okay, so let's go back quickly to the empirical results. So both offline and online agent workflow memory, you call it AWM throughout the paper. So they perform comparably. When you compare it to Mind Act, for element accuracy performs better, but has lower F1 scores. What do you attribute that to?
Yeah, so this is more of a conjecture that we didn't like do a very thorough analysis on this part. But for element accuracy, our methods gets higher. I think the reason is we explicitly extract out those example specific context from the examples. So this is due to one of the model sort of bad behaviors that if you provide in context examples, they will often just copy the things in the examples you provided. Other actions were the context. So, for example, if in the context I have an example that buys this cat food from a particular brand, but in the task query that I asked you buy a water bottle, the model will sometimes just copy the brand of the cat
Oh,
food and
okay.
when it's responding. So extracting out those example specific contexts and we replace that with the more abstract name like product name, the model learns not to copy that, or copy that doesn't really make the action executable. So I think that's the major reason why element accuracy increases. On the action F1 side, our conjecture is because we provide this workflows that basically tells you, a series of actions to do given a state, then the model may just like bluntly follow those workflows without even thinking about, oh, this is the correct workflow for me, where is my or anything different from the workflows. So sometimes the model may be just bluntly biased by those workflows, and that will cause the action F1 to be dropping a bit.
So is that, I'm skipping ahead here, but is that maybe a future work is the agent be able to determine what would be the appropriate workflow for a given scenario?
Yeah. I think that would be an interesting thing to study on, and we don't actually know too much about it yet. Because if you think about it, it's a pretty hard thing to do because this workflow thing, there's no annotation, any data set that you can provide supervision for it. And even if you say we can annotate workflows for this data set, but the workflow, the granularity or like other aspects could be presented in various forms. For
Yeah.
example, by cat food on Amazon, I could like induce a workflow like buy cat food, just buy cat food specifically, or I can use a workflow called buy a product, which extract out the cat food thing. But it's both useful depending on the user actually. So for example, if I only buy cat food at Amazon, the first one obviously better for me. But if I buy different things on Amazon, then I might have to extract that out. So the design of the workflow is also pretty tricky. In that way, it's just a lot of exploration. But yeah, exploring what is the best workflow representation and how the agents should, or what their agents should rely on to pick the correct workflow would be pretty interesting questions.
Yeah, that's interesting. I don't know how you do that without the human part of it, or at least the data set showing the way people prefer to do something or the way certain workflows are better or produce better results or more optimized or something without having that kind of information first.
Yeah, totally agree. I think for, in some sense, this workflow induction process at least is more like a data-driven approach. It very heavily depends on what data that you have or what task queries the user asks. I found this is the data availability in academia is a little bit restricted. We don't have a lot of user data. But in contrast, companies have a lot of user data. When I've talked to them, they're more like, oh, actually, due to like legal issues, we cannot directly use this user data.
Mm.
So yeah, there's also we need to figure out a way to learn from this useful data.
Right. Okay. Amazon probably knows exactly what people have typed in to search to get to the desired result, all the steps that they took. Okay, that makes sense. So the agent will learn, like you mentioned, these simpler tasks, and then it'll gradually learn more complex tasks and kind of this snowball effect. Considering that, how scalable is this approach in terms of both memory and computational resource requirements?
First, I think computation wise, because we add an additional memory to the agent, so it costs a bit more. But at least in our work, we intentionally limit the number of workflows per website. So it's, I think, on average 7.4 workflows. So we keep it as minimal so that it won't require a lot more computation cost. I would say in general, the added computation compared to the original cost you have to run this agent is not that much. And but I think scalability wise, I really like our method because it does not specifically apply to a particular website or a particular domain. So this method is generalizable across different websites, whatever the task you want the agent to do. So in that sense, it's scalable.
I'm curious on whether something like agent workflow memory conceivably could have agents that are performing better in domains that they haven't been explicitly trained on, but because they've induced these workflows that are applicable to a novel situation.
Yeah. I think, yeah, compared to a static agent where the memory never gets updated, if you apply that on a like unseen website, then our method, because we like basically adapt our memory after each time the model solves a query. So it just learn while it's solving tasks. So the if you imagine the curve system representing the agent internal abilities, the baseline static model may be like this. So across the course of solving all these queries, it doesn't really change. For
Mhm.
our model to gradually learn some workflows and get more skills. So yeah, in that aspect, I think our method could perform better than baseline methods. But I think overall, let's say if the model is previously trained on some websites, I think the model performance overall, even like whatever method that you use, is still gonna perform at least slightly better on the seen
Okay.
websites and unseen websites because of the like data training.
That's interesting. Okay. So we talked a little bit in a previous conversation, very briefly, the idea of collective agent. This paper is on a singular agent, but the idea of collective agents potentially with this idea, agent workflow memory, maybe learning from each other's working memory or something like that. What are your thoughts on that?
Yeah, I think like collective memory, where people call it like multi-agent system, is interesting. I haven't really done very in-depth analysis on multi-agents, but so there are two scenarios. So for some tasks, for example, on this web arena, you could just design um single agent pipeline that'll make everything work out. So in this way, it's similar to how you do tasks. Say if I could just do this task perfectly well, I don't need others to help me. That
Okay.
might just like more time for communication and other stuff. There are tasks that I do think requires multi-agent to do, especially like you said, different agents have different memory states. I think there are a lot of interesting works about, especially on the social intelligence of agents.
Mhm.
So, but I think one key of multi-agent system is different from single agents that you only have access to your own mental state. For example, I think in some social tasks, this agent can observe something, but is not very communicable to other agents. So they have different observations. So that unique observation or the context they have access to gives them unique roles to play on so that they could collaboratively solve something. But applying our agent workflow memory to those multi-agent settings that maybe you can imagine a bunch of different agents sort of operate in a company style and they have different roles. This is the project manager and this is
Yeah.
software engineer. They have different skills doing different stuff, but they communicate with each other to collectively solve a big project. Yeah, that would be interesting.
Yeah, I mean, particularly since you said, even though generalizability is like one of the goals, at least as far as you see, they'll still work better on data that they've been explicitly trained on, or domains or sites in this case that they've been explicitly trained on. And so, if that holds true, but then you have multiple agents working together, that bring that explicit knowledge to the table so then they can kind of share that explicit knowledge with each other. It'd be, I think, really interesting. So you mentioned a couple areas, maybe this collective agent thing, and then the model being able to select from a set of workflows which workflow would be best in a given situation. Are there other areas of future work?
Yeah, two things I'm thinking about. One is for our work, we're mostly, implementation wise, still prompting. So we didn't do any model training. It's similar to just like short-term memory. You immediately learn this task and you just put it in your head and then just apply it. You continue solving the task. But imagine, say, you have this agent on your web browser for 10 years. Then you have done thousands of tasks, then it'll be expensive and I think impractical to remember all those workflows just in context. So they're maybe shifting that to a long-term memory. You can do some sort of agent training with memories. So instead of explicitly saying that in the context you provide to the models, maybe integrate that into the neural embeddings of models. So just store that in the implicitly. One of the things that I want to build is a long-term memory agent that could reside on your computer for 5 or 10 years that learns from your trajectories particularly and know like work best for you. So it's a personal assistant. Yeah, that is pretty interesting.
Yeah, that would be very helpful. So tell us, what do you have coming up? Any research coming out that we can look forward to?
I haven't really started working very concretely on the next project, but I have another project which is a bit different from this web navigation scenario. But I'm trying to explore different interesting tasks that can be solved by generating programs. So one thing that I've been working on is having agents to do some designs on some structured visual things like websites or presentation slides. The reason why I'm interested in particularly slides is because it's a very common task. A lot of people doing different jobs, they could benefit from an agent that could automatically generate slides for them. But there are some challenges on those, the visual layout of the slide. How do you make that visually attractive? But also more importantly, if you bring those design principles in mind or you want to convey some insights with their slides. So that's more meta stuff that can the agents do it on par with human. So that's an interesting scenario. Another thing, this is not led by me, but another coworker at our school is similar to the collective agent, the agent company stuff. So we're thinking of having this scenario where you have a bunch of different agents doing different tasks. So that could be an interesting scenario too.
Yeah, I'm really excited to stay up to date on that one. That sounds really interesting. Okay, well, thank you again for joining us, Zora, to talk about your paper, Agent Workflow Memory. I appreciate your time.
Cool. Yeah, thanks for having me. It was a lot of fun.